Hello everybody to this video presentation. Thanks for taking the time to join me. Today we're going to be talking about a concept I called scaling the realms. And this is having to do with increasing security and strength of a decentralized protocol with the intent of attracting additional interest and value into the network. And we're going to do this by looking at non-deterministic security for the sharded transaction threshold signature vaults that are being used by Thorchain. And we'll get into all of this. A little bit of background on myself. I have been in this industry and community for 11 years. I've helped organize the Canadian West Coast blockchain community. Beginning in 2012, I hosted many events, dozens of events, and presented at many events and conferences all through the years between 2012, 13, 14, 15, and 16. I've supported several early projects, including my own. I was a startup founder. We were able to attract venture capital backing, and I participated in a Silicon Valley accelerator known as 500 Startups, blockchain and tech consulting for many different startups, as well as venture capital and Fortune 500s. And I'm talking about many large, specifically auto manufacturers, funnily enough, like top 3 auto manufacturers in America, top 2 auto manufacturers in Europe, as well as large package distribution and delivery companies as well. So I've got a decent amount of knowledge and a broad spectrum in both technology and business. Specifically, I've contributed to developing many different Web3 and multi-sig wallets, as well as ERC75JS, including Thorchain. Full disclosure, I did make some contributions to one of the Thorchain wallets, AsgardX. A brief history of blockchain to get us up to speed with whoever isn't watching this. It's been 14 years since we've begun this journey. We've got additional composability now available through EVM type chains, as well as application specific chains with Cosmos. We've got much better consensus mechanisms for scaling and cost and improved decentralization. We've got the interoperability between blockchains with Cosmos IBC, and we've got now sophisticated DeFi since Binance did their DEX, at least as an implementation of the concept of a DEX on blockchain as a sovereign, self-sovereign, application-specific blockchain. And now we have inter-protocol, interledger DEX with Thorchain. This is very, I say, groundbreaking achievement in the evolution of the blockchain technology. So what are the core concepts we're going to be covering here in terms of technical relevance and how we're going to address potential improvements? Several things that are quite unique and groundbreaking to the Thorchain protocol. The TSS SIGs, these threshold signature routines for their multi-sig accounts, are far superior to simple protocol-based multi-signatures or like multi-sig contracts even. So this gives a tremendous improvement over what people were struggling with multi-sig. This is super important because you actually have decentralized transaction signing for and governance over account management among parties of interest on any chain that can support it. Proof of bond, this concept that I've been calling proof of stake plus, this is, I think, a really important watershed moment in the evolution of specifically proof of stake. The fact that there's non-determinism and there's a competitive and term-limited validator set puts this protocol in terms of decentralization head and shoulders above, I think, from what I've tried to find, the vast majority, if not all, other proof of stake consensus protocols. So this eliminates major concerns with the static validator sets and long-range economic attacks due to that, and with standard like on-chain delegation for like your basic Tendermint proof of stake, and also the fact that they took delegation off chains to increase, it increases privacy for the stakeholders. It eliminates the ability for, let's say, in-band collusion for potential colluders to communicate through the protocol by learning about each other just as stakers, even not even as node operators. So that's arguably an improvement as well, especially for those coming from proof of work. I think it's kind of important also to note with this proof of stake plus that it's quite obvious, and to anybody who understands, that gets down into it, that the developers of the consensus mechanism were looking to address issues that they saw and that other people coming from the proof of work side of things see with proof of stake. So this is, from that perspective, certainly a major, major improvement. And at least with the adding of non-determinism to the validator set, it's a really important step in the evolution of proof of stake towards more decentralization. So my thought is that there's probably no more decentralized of a consensus protocol for proof of stake right now. We also have a minor thing that a lot of people don't pay attention to, which is the protocol operated treasury. This is really important if you want to have like more sophisticated DeFi and tokenomics. And the other important thing that is not stressed enough is the fact of how the issue of bridges is solved, is that the Thorchain network creates a full network overlap for all supported chains, for all supported networks. And this is because every single Thorchain node operates as a fully functional node for all supported networks. So there's no bridges, no oracles, and it's a fully self-sovereign DEX. Technically, it doesn't rely even on the full consensus of Ethereum with just a portion of its known nodes. It needs the full consensus of all validator nodes on the Ethereum state before it considers it valid and final. So that's increasing. That's like just a tremendous amount of security comes from all of this. And like this is why, to me, like this is altogether at least is a holy grail achievement in the evolution of blockchain technology. It's a first in the space, and it's unlocking new possibilities because this protocol addresses major concerns with proof of stake, multi-sig, and DeFi. So the privacy of stakeholders and node operators, that we have improved decentralized and non-deterministic consensus. So we've really addressed protocol risk from complex DeFi exploitation, which is where you have so many possible permutations for interaction with your own protocol that you can't necessarily rule out some event wherein which somebody could figure out how to exploit the protocol itself and introduce that into gaming of the consensus itself. So that's the reintroduction of tail risk into a DeFi protocol, and this is harkening back to Nassim Taleb, the issue that really decentralized applications are solving by the elimination of centralized points of control. And we also have another big thing is source chain decentralized pool management. And this is what allows for native to native exchange, because the pools are operated on chain of their origination of the asset through the TSX decentralized consensus over outbound transactions. And this is a tremendous improvement. So a water point of innovation for the whole industry. And if you think about the fact that sophisticated DeFi can reintroduce tail risk, and that pretty much negates the value proposition of decentralized applications in a way, unless this type of solution is developed, there is no potential for DeFi. So this is really that big of a deal. This kind of innovation, especially combined into one protocol from in multiple different areas, is a massive achievement. So we're going to take a bit of an approach here towards, always understanding that, of course, no software we ship is ever perfect out of the gate. We need to continually improve it, and especially at the early stages, we need to keep security as priority one, and we don't want to just create feature bloat as our desire to create more bells and whistles to sell. And community and user feedback is super important, obviously, in crypto projects where there's not a lot of organization and especially with Thorchain being the fact that it's just a highly technical project at the moment, and that is good for the security of the project and for the performance of the protocol. But of course, it's not oriented around mass promotion and those kinds of things. And unfortunately, a lot of projects that aren't as quality in terms of tech will spend a ton of time and effort on promotion. So quality projects probably, should really think that it might be a part of their responsibility to make sure that for the industry as a whole, that we need to match some kind of effort in that regard. And we really like the community giving feedback because people are showing that they care, and there's a strong community engaged with this project that I think is not so much as interested in just normal crypto hype, but sees this as a way for facilitating a great deal amount of increased security and trust for exchange of crypto assets. So the success of the protocol is going to always come down to, of course, satisfying the market in some way. And there's a lot of opportunity, of course, we want to take advantage of for improvements. So we're going to look at something that could be improved, which is that there is a lot of disruption caused by blockchain technology. And this is creating some scenarios for attacks on the Thorchain vaults. And the Thorchain TSS vaults are sharded and distributing vaults, a bond across said vaults and authority over redemption and transfer of assets out of the Thorchain pools to designated recipients. And there are certain circumstances, as currently now, the bond is the guarantee against the negative performance of the participants in the vault, and such that there is a negative ROI in on-chain terms, but I don't think this fully accounts into considering of attack vectors where returns could be gained either out of band or over time. So these are primary areas where I think that there is opportunity for ROI outside of just the direct incentive to take the bonded capital as liquidity in the vaults. And that is, and any protection of existing territory by incumbents could be seen as, a threat to existing value, and if protecting that value is a positive ROI. Just claiming that the bond is a sufficient disincentive is insufficient in that scenario. And there are, of course, many people who would like to put negative attention onto DeFi in general, and many hostile existing participants in the traditional realm of finance, let's say. And even irrational economic attackers cannot be properly discounted. So my issue that I'm pointing out here is that existing liquidity pool vaults rely on economic security alone during scaling, which I'm claiming is insufficient to cover these general attack vectors. So, and that is resulting in this concept of the minimum viable attack. So the current vault generation method distributes bonds across vault to balance collateral, but is fully deterministic and straightforward, making it trivial to predict which nodes will be in the vaults. Arranging bonding values of colluding nodes can guarantee that they are put into the same vault on the next churn. Attackers only need to submit standard and correct bonding transactions to adjust bond value to the network prior to the vault churn block. The number of nodes required is equal to the same number of minimum signatures required on the TSS vault accounts. So as it is right now, you put your nodes in, you get your nodes in the validator set, you arrange them as such as they will be shuffled or just assigned into vault groups based on, every nth node being in the bond group, and then as long as all your bonds are every nth node, then you're going to get into the same vault. So the main contention here of all of this is that the minimum viable attack vector is accessible to certain types of hostile actors prior to the large-scale protocol growth for economic security to be relevant in the global context, which inhibits the network's growth. And but I mean, what I mean by global context is that Thorchain is essentially economically secure in the economic locality. So in terms of other protocols that are the same scale, or participants in the protocol itself, or other participants in other competing protocols within that economic locality, the economic security of the Thorchain vaults holds. But it's when you get out of that economic locality and move into the global context where the amount of bond lost could be seen as a loss leader for protecting existing territory, or gaining advantage in a future project or what have you. So there's a couple different psychographic vectors for this short-term irrational ROI, such as what I call the economic suicide botter, or the script kiddie hacker, cryptimaxo radical, who has lots of unearned crypto, who believes in the hacker ethos, and who believes that what can be hacked should be hacked, and therefore if there is a vulnerability, it needs to be exposed as soon as possible, such that further dependence on that vulnerability isn't created. So also maybe there are people with lots of wealth and lots of value, multi-billionaires, who just really don't like what this technology is about, or feel it's really offensive to them in some manner. And then the other direction in which you could get ROI is long-term. So that's disruptive incumbents, meaning large-scale organizations in the financial industry, or large competitors, or up-and-coming competitors in the DeFi space, who would like to besmirch a protocol to gain their advantage or such. So the main contention, as we're saying here, is there are attack vectors that are unaccounted for in the current economic security model of the Thorchain sharded bonded vaults scheme for the governance over the pools of liquidity that are being managed by the protocol. So what is the effect of this? What is happening as a consequence of this? I believe this is creating what I call the economic security chasm. And that is basically boils down to the fact that it's just scaling the network when you still have some relatively low node and bond. The potential for this attacks are much greater, and they begin to happen as soon as you begin to shard the vaults. And we could say that maybe Thorchain is now approaching growth phase 3, where there are 5 vaults, and there are 12, 13, 14 signatures per vault. And at that level of ability to collude very easily and directly into the vaults, in the global context, this is the maximum vulnerability. Of course, as the networks scale and it becomes like 10 or 100x harder or more costly to get the nodes and the stake you need to collude in the vaults, then you've achieved economic security within the global context. But until that point, there is economic vulnerability. And this is causing what I see as a security through obscurity growth conundrum. And that is, as the market and brand awareness grows, so does the probability that a person or organization who could benefit from such an out-of-band or economically irrational exploitation, then the increase of the opportunity for the attack also is increased. At a certain scale, we do reach sufficient economic security, and this window of now is the economic security chasm. And if there is increasing growth in the network from additional tooling or services for greater convenience in participation within the network, this also lowers the barrier for attackers to join the network as well. So this is even more relevant as new protocols start using the same vault management scheme. So this is, for instance, like Maya is the new protocol. They're going to start out, of course, with all validators participating in signing of the vaults, which is good because of the non-deterministic validator set that they're inheriting from the Thorchain protocol. But as soon as they begin to shard vaults, then they will also run into similar economic security problems. So the challenge that we're going to take here is that we are going to attempt to preserve or improve the bond balance across all vaults. We're going to attempt to add non-determinism to vault assignment for nodes to eliminate this minimum viable attack vector, and we're going to look for various sources of entropy in balance with limits on control and manipulation to prevent any simple or direct collusion for attack to organize attacking nodes into any particular vault. And our hypothesis is based around what we see as here as increasing the economic time and cost of vault collusion greatly discourages out-of-band ROI vectors during scaling of the network and liquidity, especially if we eliminate the minimum viable attack vector. This improvement in security should increase trust in the protocol. And with communications and support, this should result in increased network engagement, hopefully from bonders, network participators, and even liquidity providers. This growth in the networks, of course, increases the security generally. And importantly, we want to use this method of non-deterministic vault generation to increase at least far greater than linearly. So then this initiation of the network of growth, a network effect for security growth, is going to help us support the bridging of the economic security chasm with this positively self-reinforcing feedback loop of increasing security in the Thorchain vaults. Now, it's important to understand, of course, there are people who see, like, there is existing issues with trying to add non-determinism to proof-of-stake decentralized application, and that is when you add non-determinism from a source that is manipulatable and which adds incentives for positively participating participants that can lead to advantage to those who would attempt to brute force such sorts of entropy, and in gaining such advantage require those other positively participating nodes so also engage in brute forcing just to compete with and maintain pace in the network, which is of case when the consensus can devolve back to proof of work. So we're going to fully consider and count that when we're talking about this method of non-determinism for generating the Thorchain vaults. And we want to just take a brief moment here to understand why this can work and why the unique characteristics of this protocol support that. First of all, the related method is executed on a very slow cycle. The vaults are churned once every 3 days approximately, or 7,600 or so approximate blocks. And it is not related in any way to block production. And it does not affect the economics of the DApp because there's no added reward or incentive to game the method for any positive participants because there's no advantage to being in any one vault or the other for any standard participating nodes. You don't get any additional returns. So, standard participating nodes are looking to reduce cost, to increase ROI as much as possible, and there's no advantage here, so there's no threat of any devolution of the protocol into proof of work. And it's really the biggest thing about why this works is that there's more entropy available to the state machine that can be manipulatable by attackers. Right? So this is only possible because of Thorchain and the non-deterministic validator set. So let's look into our solution here. Non-deterministic vault sequence shuffle. So what we're going to do is add a non-trivial subtle to the vault sequence for each round of delegation of nodes to a vault. The order by which each node is to be assigned to a vault is randomized, while maintaining its average equality of bond distribution between all vault groups. So we've, this challenge of the proof of work is eliminated, of course, because we have no economic advantage in the protocol. There is no way that this is involved in any standard block production or any rewards gained from any block production or any participation in the protocol itself in any way. So the only people who are going to be, the only entities interested in gaming this shuffle are going to be attackers as they try to collude for control of the vault. This is a layer of security in addition to economic security, meaning that failure of this method is still backstopped by bond slashing, etc. And as well as importantly, we'll look at how this improves bonding distribution. So the value proposition of all of this is to eliminate the minimum viable vector of attack for collision of bonds and improve the bond distribution across vaults, increasing economic security while not affecting decentralized application economics, and utilizing and leveraging the unique sources of Thorchain's own unique characteristics in the dynamic non-deterministic validator set. So now let's look at the shuffle method. In taking hex bytes as a string and resolving them into a series of combinations of permutations, where every permutation is of n length and n depth, and number of combinations equal to the total number of validators divided by n rounded up, where n is the number of vaults to be generated. These random bytes are generated by performing a standard cryptographic hashing of sources of entropy from non-deterministic data available from the current state of the blockchain in the network. This shuffle provides a significant range of possible solutions, and as a given random source cannot be reverse engineered. So there is no way to go backwards and figure out where your nodes would need to be in order to be shuffled into the vault. So let's take a look at our sources of non-determinism. This is super important because of whatever shuffle method we're using. We want to make sure that our sources of non-determinism cannot be gamed. So we're using the block hash, we're using the block time, and we're using the validator set. And these are in ways that are manipulatable by some part, and in many ways known by existing security protocols within Tendermint, for instance. And we can get more into that as we talk about the balance of entropy. So the point is that we want no single source of entropy to solve for any sequence alone. As you're attempting to get your vaults, your nodes into the vault, you're going to need to arrange them, pseudo-randomly according with the sequence that's going to churn them into the vault. And if you were to be able to have a significant sufficient source of entropy to manipulate, then you could literally just leave pretty much your vaults, your nodes where they were, generate this source of entropy that you would know would lead to them being churned into the vault, and then they would get into the vault. But we are going to limit any source of entropy and the ability to manipulate it such that that cannot happen. Also, any single source can thwart the control of other sources. So regardless if you can fully control two of the three sources of entropy, say for instance, that's not sufficient enough to not be thwarted by the third source of entropy. And we want to use non-manipulatable entropy to guarantee that there's a non-deterministic outcome for the vault, the generated of the vault groups. And we're going to use tuned values and tuned amounts of entropy from all of the sources in order to do that. So if we look at the block hash and the block time, the slash points, the node score, the node rewards, the pub keys, and the bond values, you'll notice importantly that the block hash is very, very low. And this is not to scale accurately, it's approximate for representation here. And what that is for instance, in the use of the block hash as a source of entropy, it's obviously a very, very small amount of entropy, and it's just used as a salt really to thwart full control of other sources. And what this means is that the only node that can actually control the block hash is the block producer, or the block proposer, pardon me. I don't want to get too much into the specifics of Tendermint consensus mechanism. I'm going to assume, then this presentation is going to assume kind of a knowledge around that. But essentially, the block hash is essentially irrelevant in terms of your ability to manipulate yourself, your attacking nodes into the vault. But it's there to ensure that if you are not a proposer, then the other nodes who are not a part of your attacking cohort will just inadvertently and by natural process thwart your attack. So what this means is that if we're using not only that, the block time, but slash points, which cannot be fully predicted by any block proposer. If you're to be a block proposer or a participant in some kind of colluding endeavor, the only way that you can arrange your nodes into getting into the vault groups are now pseudo-random, and you have to be able to essentially predict the state of the chain and the network at the time of when the block that's going to be used to generate the next vault churn and is going to use said states of entropy will be at that point in time. You have to know what the state is going to be in order to predict the sequence. And if you can't know that because you can't actually fully predict the block time is the mean of the signers in the rounds of signing that is ongoing by the Tendermint consensus engine. And you can manipulate only to a certain degree because the Tendermint consensus engine specifically, handles any significant manipulation of block time. And so you cannot fully control the entire state of entropy that's being used to generate the random shuffle vault sequence. There is no 100% solution possible to be derived at any point in time. So that means that any single, attempt to collude into the vaults is now reduced to pure probabilities. And by distribution, through the distribution of this, obviously, we've covered that. But let's look at the effects here of this particular message. If we're reducing it to probabilities, then what are we talking about? We've got a total potential number of shuffle sequences for all the nodes to go all into the vaults. We've got that quite high at 7 times 10 to the 40th. And the total entropy we have going in from all of our sources is well over that. So we have plenty of entropy to generate all the number of potential sequences we would possibly have for full non-determinism in the vault so we can shuffle. And then that means there's a base probability, since even just having if all nodes are being randomly churned into the vaults, then there's a base probability over how many churns that your vaults would just get randomly churned into the same vault. As long as you were properly distributed amongst the vaults, then that's, a really high probability here. Or pardon me, a really low probability, really low odds, which is 1 in 244 million. So that means the average time to churn in is 1 in 1 million years. And we also go into what a fully coordinated attack, minimum viable attack vector it looks like. But even with this, we're still at 12 years. And this is assuming, 5 vaults or 12 minimum SIGs with maximum attacker advantage. So this is pretty much maximum vulnerability of the protocol and the vaults with maximum attacker advantage in a fully coordinated attack. That's still going to take an average of 12 years. That means because we've created a scenario where every single shuffle outcome is based on pure probabilities, the only thing you can do is try to reduce those probabilities. And even with the full capabilities of all your nodes to manipulate all sources of entropy, you're still only going to have, an average 12-year wait until get into the nodes with your minimum viable attack vector. So we can get deeper into all of this here, of course. But let's look at how the linear vault assignment currently works. Let's get into the brass tacks. So given nodes 1 to 12 assumed in order of bonding, they're distributing groupings of nodes but for vault signers from greatest to least iteratively through the groups. So this actually results in the groups having maximum disproportionate bonding from this type of method. You can see if we're distributing the vaults, group A here, because it's always getting the higher value bonded node in every single round that's being distributed as it goes through assignment through vault A, vault B through C, then it assigns another node to vault A, and then another node to vault B, and another node to vault C. As these nodes are being assigned with the current method, the higher bonded node is always being, of whatever round of assignment that's happening, is always being put into vault A. Importantly, when you look at distribution of talent in like sporting associations, they will always reverse the draft order. When they're drafting new talent into the league, the draft order is reversed, and that actually equals out the bond value. So right now, the way the current vault is being assigned is very simplistic. and is not optimized for normalization of distribution of bond across the vaults. And if we look at actual data, this is existing data taken just a short time ago of the different bond values that are being in the different vaults. We have 5.5% difference between the different vaults. So what we're going to do instead is for each number of nodes, the number of nodes are randomly shuffled by their rank across the groups, where n equals the number of groups. This is better distribution than just linear unidirectional left to right assignment. So here we can see that the nodes, like the highest bonded node ended up in group B randomly, and the second to highest bonded node ended up in group A randomly, and third ended up in C randomly, and same with the next iteration and the next iteration or next iteration. And we can see that through the summation of these groups here, very simply, that our distribution is much better in terms of bonding. And we can actually apply that to existing vault data, which I did. I took existing vault data and I applied the shuffle method to it, and we've reduced the let's say, deviation from the mean from 5.5% to 4.36%, which is a 20% improvement in terms of total deviation. So this is, I think, indicative of this being, regardless of even the security properties of the vault shuffle itself, an improvement on existing bond distribution and an improvement to economic security. So what we're going to do now is, before we get into like additional concepts that would help secure this, we can go to take a look at some headline numbers as to what would it look like for total probabilities and the specifics about how it is that you're going to churn into the vaults now. So we're making some assumptions here to make the total number of validators easy for us to reason about, being 100, and also giving you the different percentages and odds that you're going to have to get into the vaults. So now we look at the total number of shuffle sequence combinations for this vault setup, which is we have a total number of 5 vaults. We have 12 minimum signatures, and there's going to be 20 nodes in every vault. And this gives us a total number of shuffle sequence combinations of 3.8 times 10 to the 41. So 3 plus 41 zeros will get you the number of combinations, and this is the number of sources of entropy we have. This is the sources of entropy we're taking, and these are just simple bits. This is this is not the powers of bytes. This is just simple bits of entropy. So we are only using, for instance, like F3 would be 2 hex digits, and that's 256 bytes of entropy, and that's all we're taking from the block hash. From the block time, depending upon the assumptions you're going to make for the standard deviation that the Tendermint consensus agent allows for, we're looking to assume here that we have 28.2. Where we get a ton of entropy, of course, is from the validator set. And we're assuming all minimal amounts of entropy that we're gaining from the validator set, such that we cannot in any way overstate the security of this method. So that gives us total entropy, net entropy for all the sources, and we have some general assumptions for the economics, very rough at this point in time. So now, to look at where we're looking up for the costs and the time to get into the vaults, with this setup where we have 12 attackers arranged such that they can be randomly churned into the vaults, and with just us sitting there waiting to see how long it would take for us to get into the vaults, obviously this is where we get, 1 in 244,000 is the odds that you'll get into the actual vaults, and given that that's once every 3 years an average distribution of probabilities, you're going to get 1 in 1 million years wait time. This is obviously astronomical. This is obviously never any kind of practical way to think that anybody would get into the vaults just by sitting there. So now we look at, if we manipulate certain sources of entropy, so we can control the block hash, but we don't control the block time or the validator state, and we're still just going to try to increase the probabilities of us getting into the vaults in that manner. We still can only reduce that down to 1 in 32,000 years. If we're manipulating only the block time, that's even worse because it's 1.5 million years. And if we manipulate the validator set with all best prediction assumptions, meaning that you actually get lucky on thinking what other validators are going to earn in terms of their slash points, then you can get it down to 1 in 100 years. And if you combine all your manipulations in terms of how you're going to control the entropy and project what it is that the state of the decentralized application will be and the consensus of the state machine, you're still 1 in 441 odds, and that's an average wait time of 15 years. So now it's really important to understand, I think, that if we want to have a method where we're using non-determinism to increase the security of the vaults by preventing people from figuring out a way to even get to their colluding nodes into the vaults, how does that scale with the network? And importantly, it scales greater than linearly. So if we just increase the number of minimum signatures on one vault by 1, we've gone from all our baseline numbers here on full manipulation to 61 years. So nicely, this method, due to the fact that essentially the minimum signatures is the exponent on the total amount of possible sequences, then as we increase the number of minimum signatures on the vaults, then our probabilities go way down. So resetting this to 12 now, of course, we could think we could add extra attackers to increase our probabilities. So we added another 2 attackers, so now we're up to 14 nodes. And this will reduce the probabilities down in this certain scenario of assumptions down to 2.5 years. And it's also important to note that due to uptime on nodes and everything as such, in terms of churning in and out of the validator set, you're going to start to require additional nodes. Just to maintain the 14 nodes you would need to attack now, you need to have 15 nodes. So we can see as we increase the number of attackers, we can reduce the probabilities down to increasingly normal levels, to where we can get down to 1/2 a year with now 17 attacking nodes. But it's also important to realize is that the protocol rebalances, I think, approximately rounded up 2/3 of the SIGs. So as you get up to 21 nodes per vault, you're actually going to be at 14 signatures, or 14 or even 15 signatures. So as you see, as a network scales up, even by the amount of extra attackers you bring onto it, the security of the shuffle also scales up. So now this is, let's say, a very still somewhat rough analysis of the total security model. There are potentially other improvements that I know could be made to some of the assumptions, as well as some of the methods here to increase the resolution of our analysis. But in having done so, 1 or 2 times now, I'm been sufficiently convinced that my assumptions are so ridiculously on the side of attackers in any way, that in any place where there's any ambiguity, that increasing analysis should result in us getting a better picture of just like how secure this method is then. So those are all our baseline numbers, and those are analysis. So there are other ways, of course, that could also increase the security of this. Important to note that since we're using the validator state as an input as a source of entropy into generating the vault shuffle, any positively participating a node can merely make a change at any last minute to what they might think do is disrupt any potential coordination into shuffling into the vaults by disrupting the state through either changing their bond value at the last moment or by even, maybe intentionally earning a slash point. It's possible. We could also look at ways by which both attackers could manipulate the validator set by limiting the amount of bonding transactions per block. So this is also something else that could be considered to even further increase the security. So as we wrap it up and we look at what it is that is, the really supportive protocol characteristics that make this possible, there's no disruption of block production on a relatively rarely occurring method that does not affect decentralized application economics at all. And based on the fact that Thorchain itself has the actual source of entropy that makes this possible, and that is the non-deterministic validator set. And really, at the end of the day, if you also consider that manipulation of block time will necessarily be towards the anticipated expected average, because you have to project what you think the block time is going to be in order to anticipate where your node should be to be shuffled into the vaults, and you can only ever really assume something that is somewhere around the average. And so manipulation in terms of block time would only actually increase regularity of the network. And the shuffle method itself, regardless of its own security, increases the economic security through better normalization of distribution of bond across the vaults. There are some limitations. The amount of combination of permutations is proportional to the relationship between your minimum signatures, your maximum signatures in the port, and how deep, how great of a depth you're going to have then to draw from in generation your total vaults. This is why we have to include more than just any single source of entropy. We also need to acknowledge that lower minimum signatures in vaults reduces resistance to solving for a sequence, but greatly scales as the signatures increases. So we're looking at a minimum, like the minimum should be 12 signatures, and it's nice to have 5 vaults to start with here. So in conclusion, Thorchain, as well as other protocols, will face a crossing of the economic security chasm, a time during which a hostile economic attacks by collusion in the pool vaults is possible by attackers gaining return on investment externally or over a long time horizon. This method is intended to eliminate at least the simple minimum viable vector of attack, and it significantly increase the economic cost over time by a hostile validator nodes beyond viability during scaling. So this is in addition to the approved economic security, which still exists. It is not disrupted in any way by this method. And this should hopefully successfully, if done well and borne out to be valid and shown to the market to be increasing of security of the vaults, help growth of the network, and support it in crossing the economic chasm. So there's lots of questions we can do on specifics that we need to address, and there's more to come obviously in a lot of this stuff. So thanks everybody for tuning in. I hope this was of value and information for everybody to learn about, and there's obviously a lot more that could be discussed and shown through this. There's also a corresponding GitLab issue that is related to this that I am also authoring and managing. So thanks for your time and have a great day.